Hi everybody, in this chapter we are going to start thinking about the functional group, which is a double bond. It's the carbon-carbon double bond, which is present in a variety of organic and biological molecules and will probably help you understand why tomatoes are red, carrots are orange, or flamingo is, well, flamingo. We also will take a quick look at what will be the consequences of the stereoisomerism. So, for example, if two groups point on the same side of the double bond, what does that mean and what are the implications of that? We'll get you started on mechanism writing again, so some of the concepts are going to be similar to what we have already seen in the last chapter, but we are going to build on it now. All right, let's get started. Sometimes alkenes are also called as olefins, which, believe it or not, according to Merriam-Webster, means a synthetic fiber such as polypropylene derived from an alkene. So when we use the word olefin in layman terminology, we are essentially suggesting that it contains an alkene. Of course, we know now as students of organic chemistry that alkene means that there's got to be a double bond. So the word alkene itself means something, okay? When you think about where you might find alkenes, you would find those in flavors, fragrances. I talked about the tomatoes and the beta carotene. In fact, talking about beta carotene, I think life itself would be impossible without alkenes as beta carotene. This compound contains 11 double bonds and it's an orange pigment which is present in carrots. It's an important dietary source of vitamin A and can offer protection against some types of cancer. You might wonder, well, why this chapter then? Well, that's because this is kind of like a door, opening a door to other functionality. Because this is a reactive species, as in the second part of this chapter, we will talk about several reactions that we will see for these alkenes, and that is going to increase the diversity of access to those functionality, the chemical space that we have been talking about off and on. And so if you are able to fill in the chemical space, meaning you are able to generate various diverse structures, you also are filling in the biological space, because for every chemical space you have a biological target. You may or may not know about it, because if you did, then you probably had a cure for every single disease. Let's go further and talk about the nomenclature. But before we do that, couple learning outcomes. We will be talking about the structure, we'll be talking about the stereoisomerism, and the basics of the electrophilic addition reactions of double bond. Like I was telling you, the double bond is going to open up the doors for various different functionalities, from alcohols to diol to the dichloride. We have the epoxide, the acid, the aldehyde. We have the polymerization, so the Walmart bags that you have. PVC, which is polyvinyl chloride. So if you have the vinyl chloride, you polymerize it, it gives you PVC. You have your isopropanol, which is your rubbing alcohol, right? Ethanol, we talked about, that's your beverage. Acetic acid, that's vinegar. And so there is a wide application of alkenes as a functionality, on not just as alkenes, but also because they give access to many different types of other compounds. All right, so as far as naming goes, we are going to follow the same rule. We are going to name the parent hydrocarbon and we will include the double bond. So that's the only difference. The only big thing that I want you to think about is the bright idea that the double bond is going to be is going to be a part of that longest chain. And whenever you have a ring, think about using the word cyclo, and so, or cyclo. So the rules are exactly the same, but now since functionality that we are talking about is the double bond, you want to give that double bond the lowest possible number. All the methyls and the ethyls and the chloros, they are going to be considered as substituents, because in the big scheme of things, the double bond is, being a functionality, it is higher in priority than your substituents. So it always is functional groups followed by substituents. If you have two double bonds, we will use the word diene, because you have two double bonds. Likewise, triene, polyene, so on. Let's take a look how we can think about this. So over here, I have two alternatives. I have my nomenclature, my numbers set up in going right to left. I could also perhaps think about going left to right. The only difference being, it would still be a hexene. The only difference being that my green would give the number 4 to the double bond. Notice that when you number the double bond, you kind of have to think about it as if it's like a tunnel and you have to go through the tunnel. So you look at the location of the double bond as the first atom that encounters. So in this case, it's position 2. So you're comparing 2 versus the 4. And since 2 is the lower number, that's what you're going to go with. So the name for this compound becomes 2-hexene. You could call it hex-2-ene. That's a more modern way of naming it. So please feel free to use that. Let's take a look at another one, the one I have over here. Irrespective of whether you go left to right or right to left, you would have gotten the double bond at the same location, position 3. So it is a 3-hexene irrespective. But we chose to go left to right because the methyl now is going to receive a lower number if you choose to go from left to right. The name becomes 2-methyl-3-hexene or 2-methyl-hex-3-ene. Consider that second one always sort of implicit. That is a more modern way of doing things, but consider that even if I don't write that. Let's consider the third one. This is an interesting one. So if you want to take a look at your longest chain, the longest chain one might think would be 1, 2, 3, 4, 5, 6, right? Because we are used to looking for the longest carbon chain. But now my rule is that you have to look for the longest carbon chain including the double bond. So now my longest chain becomes this one, because I'm supposed to be including this double bond. Okay, so the ethyl group here, even though the continuous connection of the carbon atoms is long, if we would have included the ethyl group, it would not have included the double bond, which is why we are going to call this a 1-pentene, the second position of which is going to hold your ethyl group. So 2-ethyl 1-pentene or 2-ethyl pent-1-ene are the two possibilities that you will have. Let's take a look at another one. This one has a diene, and the locations of the diene are the first position, of course, and the third position. Those are your two positions for the diene. We call it 1,3-butadiene. The second position holds the methyl group, so the name becomes 2-methyl-1,3-butadiene. If it's a cyclic compound, such as the one that I'm showing, of course, we know that it's going to start numbering at the double bond, right? But you could number the way I have, or you could number 1 and 2, again going through the ring. So either way, again, it is going to be a cyclohexene. And because you have the presence of that methyl group, you don't actually have to provide a number to the ring. You can just call it cyclohexene. It's implicit that you would have started numbering at the double bond. But your possibilities are that the 1 and 2 could shuttle between The 1 and 2 being one holding the methyl or one being at the other carbon. And you choose to follow the red route because of the methyl group. The methyl gets lower number. That's why that's the direction you number it in. The name becomes 1-methyl cyclohexene. If you notice the next one, it contains 2 double bonds. So this is a cyclohexadiene. Cyclohexadiene. Notice that the diene starts with a D, a consonant, which is why I'm calling it cyclohexa, not cyclohexy, but rather cyclohexadiene. And if you just leave it at that, then, well, you could have another cyclohexadiene, which would have the double bond at position 3 and position 4. And so your 2 locations that we are talking about are here and here, right? But that's not the case in this particular case. You have at position 1 and position 4. So it's a little bit different. How do you show that? You show that by putting down the number in front of the cyclohexadiene. So you could either call it cyclohexa-1,4-diene or you could call it 1,4-cyclohexadiene, as the case may be. Sound good? Let's take a look at the next one. We have cyclopentene. Hopefully you can see that. The only other possibility to follow would have been to go this route. And again, because this is a ring, you start at the double bond. You don't do that for the acyclic compound, but for a cyclic compound, you start at the double bond. And for cyclic compound. And so only other possibility would have been going in this direction. And because in this particular case scenario, you have your methyl group with the position 1, that is how you're going to go. And the name becomes, in this case, 1,5-dimethyl cyclopentene. Occasionally, I have been asked if it would be possible, if it would be accurate to call it 1, 2, 3, 4, and 5. So we would have called it 2-cyclopentene and 1,2-dimethyl, right? So let's just discuss that. 1,2-dimethyl, 2-cyclopentene. Why is it accurate or inaccurate? It is inaccurate because you're giving priority to the methyl group rather than the double bond. The rule is that you must start at the double bond itself. That becomes position 1. That's set in stone. And so for that reason, and this is specific for cyclic compounds. So for that reason, since you are right now giving priority to the substituent rather than the functionality, that would negate, right? And so that is not the appropriate way of doing things. A couple systemic names and common names, because when you're taking a biology course, for example, or even marketing, if you're in the food industry, they might refer to some things like ethylene, which is a commonly used ripening agent for the fruit. They would call it ethylene, and that's just the common name for ethene, or propylene, which is a common name for propene. Isobutylene for 2-methyl propene, and isoprene for 2-methyl-1,3-butadiene, which as a polymer is essentially what rubber is. So the entire story about vulcanization of rubber and how the Goodyear company was born goes back to this isomer, this compound isoprene units, which turns out nature makes and makes a lot of it. And there is a wide variety of natural products that are synthesized, which include a lot of fragrances, a lot of anti-insect or anti-mosquito type of material, anti-worm, a lot of natural products. They contain the isoprene unit. All right, what we are going to do in the next couple minutes is go through each of these molecules and give them a name. So what is it that you should do? Pause me. Yes, exactly right. And so pause me and then compare your answers to see if that matches. All right, so I thought that I would give you guys a flavor for what I've been doing here. Of course, I'm looking at the longest chain, including the double bond. And so since that's a 5-carbon chain, I'm calling it pentene. And the double bond is at position 2. Notice I'm supposed to go through the tunnel. So I'm calling it either 2-pentene or pent-2-ene. Likewise, if you look at the next one over, it's a 4-carbon chain. So we called it 1,3-butadiene because the double bonds are at positions 1 and 3. So either buta 1,3-diene or 1,3-butadiene. Likewise, if you look at your longest chain in the next one over, it's a hex, and the second position has the double bond. So hex-2-ene with your methyl group at position 5. So 5-methyl-2-hexene or 5-methyl-hex-2-ene. Next one over is hept-2-ene, the fourth position of which holds an isopropyl. So you can either call it isopropyl or know that your point of location, which is this bond I'm showing here, I'm calling that a 1' because that's the point of attachment. And I'll look for the longest chain. So 2' became the longest chain. And since position 1 has a methyl, I called it the 1-methylethyl. So recall, this is the complex substituent, if you will. This is the complex substituent name, the 1-methylethyl. So you could also give it the name as 4,1-methylethyl hept-2-ene, and that's okay. I'm going to go through the rest of the chain as well. Again, you're going to include the double bond within your longest chain. So this is a 1-octene this time. Third position has a methyl. Fourth position has a propyl, and you have to alphabetize it still. So 3-methyl, 4-propyl, 1-octene. Let's take a look at the next one. 1, 2, 3, 4, 5, 6, 7, 8, and 9. So that must be a nona 2,6-diene or 2,6-nona-diene, however you want to say that. Fifth position has a T-butyl. We only count the B of the butyl part of that. The T of the tertiary doesn't count. Fourth position has a methyl group, so we will call it 5-T-butyl and 4-methyl nona 2,6-diene. Or if you wanted to call the T-butyl by its complex substituent name, then this position becomes 1'. The next one will become 2'. So this is a 1,1-dimethyl ethyl. So T-butyl is also called as 1,1-dimethyl ethyl. And then fourth position has the methyl. Of course, we still have the nona 2,6-diene. And now you might wonder, well, aren't we supposed to put the dimethyl ethyl later? Recall, when there is di-tri-tetra in the complex name, then the D counts, right? That is the only time that that D counts. So you're comparing the D of the dimethyl ethyl versus the M of the methyl, which is why I placed it in the order. So what's written in green is absolutely fine. Let's take a look at number 7. So we are starting 1, 2, 3, 4. If we would have gone in the other direction, it would still have been the same numbers. So this is going to be cyclohexene, and position 4 and 5 have the methyl group. So I'm going to call it 4,5-dimethyl cyclohexene. You don't have to call it 4,5-dimethyl cyclohex-1-ene. That will be redundant. The last one is a pentene. I'm going to define the 1-pentene. And the third position basically has 2 methyl groups. So I'm going to call it 3,3-dimethyl 1-pentene. If you're just starting out and you are feeling a little bit iffy on whether my name is correct or not, a good strategy would be to try to write down the structure of the name that you just came up with and try to compare your structure to the structure that was given. And if they're the same, you probably are right, 99%. But if not, then there can be issues. So that would be one suggestion. The other suggestion to verify, self-verification, would be to number. And that goes a long way, because when you're numbering, then you are forcing yourself to count the carbon atoms. So the problems with when is it butene and when is it pentene, those are not seen. Let's write down the structures of the molecules that have been given here. The first one is a hexadiene. You should really have paused me. In case you haven't, go ahead, pause me. So I like to really draw it out and number it as I go, and then work backwards. So 1,3-hexadiene. So that's my double bond at position 1 and position 3. And at 2, 3, and 5, I have my methyl groups. This is 1, not a methyl group. So that's my molecule. That's it. They did not define an E or Z, which is what we are going to talk about later in the chapter. So we don't have to worry about it. But for now, but if this was the name that was given, then you could totally draw the structure. You could, if you wanted to, also draw out another structure that may look like this, which essentially is the same thing, just that this big group that you have is on the other side. You could draw it that way too. And that's what we will talk about when we discuss the E and the Z. All right, let's take a look at the next one. We may have just actually given the name for this. 1-pentene means this chain with the double bond at position 1. 3,3-diethyl. So I should put in 2 carbon chains coming out of position 3. The next one is heptadiene. 1, 2, 3, 4, 5, 6, and 7. 2, 3, 4, 5, 6, and 7. 2 and 5 is where I have the double bond. Position 3, position 5 is where I have the methyl. 4th position has the sec-butyl. Okay, so we have our sec-butyl position that we just connected. That's my sec-butyl. That's my double bond. And those are my methyl groups. I should be good to go. Let's take a look at another one. I have a cyclopentene. Cyclopentene means a pentagon, and at one of the positions I'm going to put down the double bond, which basically locks it as position 1. At position 3, it's saying that I'm supposed to have 2 methyl groups. So those rabbit ears that you just saw, the antenna, yep, that's what it'll look like. 3-octene, and we have a 3,6-dimethyl. 1, 2, 3, 4, 5, 6, and 7, and 8. One more. 3rd position has the double bond. 3rd position has a methyl. 6th position has a methyl too. And that's my molecule. That's it. So when you think about a double bond, what comes to mind? If you're thinking sp2 hybridized, absolutely. You should be thinking double bond, sp2 hybridized. Those are things that, buy one, get one free type of a scenario, that information. And that has 3 equivalent orbitals. And that would mean that this angle that we often refer to is going to be the 120 degrees, and the 4th orbital is going to be your p orbital. So we say that the double bond gets generated because of the overlap between your p orbitals. And so if you had a system of, perhaps you had alkene, then this double bond that you are seeing, and I'm going to now erase that perhaps, that's going to get generated because there is interaction between the p orbitals, and the p orbitals have that 1 electron on each of them. So if one had to count how many sigma, how many pi, each of these are sigma bonds because they're single bonds. But that pi-pi overlap is the pp overlap. That's going to give you the pi bonding. Now, whenever the bonding takes place, there can be additive interaction of the p orbitals, in which case you're going to see, recall from your Gen Chem 1 experience, your teacher may have talked about how the overlap, if both of these are plus, then they're going to add on, right? So that's the additive. And how if this is plus and the other one is a minus, that's going to lead to the anti-bonding higher in energy orbital, also called as the subtractive interaction between the orbitals. Now, when you think about the pi bond, the combination of that sigma and pi essentially causes and provides greater stability to the molecule of ethene. So the basic difference between ethane and ethene, as you can recall from our discussion back in chapter 3, would be that if you are considering this single bond, right, this bond can rotate. That's how we had this. So if I'm viewing as a user, that's my eye, and if I am viewing the molecule in this direction, I'm going to see a carbon atom that holds 3 hydrogen atoms, and on the back carbon, I'm going to get 3 hydrogens as well. And if they're eclipsing, or if I start rotating, I'm going to get the staggering. Long story short, I am moving this bond, I'm turning this bond, I'm rotating the bond, and hence I'm able to see the various different conformations, which, by the way, through spectroscopy, as I was telling you the other day, through spectroscopy, NMR spectroscopy, low temperature NMR spectroscopy, they were able to identify the differences between them as to where those protons show up, which is how that was like a clear affirmation and a confirmation that rotation does happen. Now, if you try to consider that for the alkene, okay, so let's say, let me draw that alkene over here. Alkene is completely plain. And if you had to actually draw out, you would see that the p orbital is actually forming that pi bond. So you have overlap between these two lobes. So while your molecule, I'm going to try to draw that out in the plane. When you're looking at the plane of the double bond is this, and the p orbitals are locking it at another plane. They're perpendicular, right? So you are utilizing, in a three-dimensional space, you're utilizing more than one spot for that interaction to take place, which is why if you try to rotate, if you try to turn this, you're going to basically break this bond. What that means is that if you ever have to turn, if you have to rotate your double bond, that will lead to breaking of the bond, and it's obviously not easy to break that. So the rotation is prevented. It's a high energy barrier, typically 268 kilojoules per mole in case of ethene. And if you break the bond, then know that you have each of these atoms go with one electron. Right, their electron will come back to themselves. So now they will be ready to interact. So that's how the double bond will react. That you will have to break the bond, you will have to twist the bond, you will have to provide the energy to that bond for the reaction to take place. All right. And that's what I'm showing you here. Both of the electrons, this is singly filled, both of the electrons are participating, should be anti. And if we give it a 90-degree rotation, then that bond essentially is broken. And so now this is a single bond that you would see.